My computer decided to update yesterday. It took 3 hours to update.
That sounds horrible.
Oh, it was so painful. Like part of first hour, all of second hour, I didn't have my computer, and then a little bit into third.
That sounds literally awful.
It started at 6:45 in the morning. It didn't finish until 9:45.
How are you supposed to teach without a computer?
It was painful. Okay, so atoms. So you were supposed to take notes on this. This was the kinetic molecular theory. Atoms and molecules are going to have a certain amount of energy. So all things right now, no matter what it is, solid, liquid, gas, everything's vibrating a certain amount. Okay, and you're like, no, my desk yeah. Your molecules are vibrating in place, okay? If we cool that down to a point where that doesn't happen, that's called absolute zero. And that's where we have a temperature scale called Kelvin. We talked about it very briefly at the beginning of the year, okay? That would be 0 Kelvin, okay? They have gotten very close to that in a lab setting, but nowhere on Earth, in the universe, no place is at 0 Kelvin right now, okay? So all of your molecules, even if they're a solid, are vibrating back and forth at a certain amount, okay? In a solid, they're fixed in those positions. They're not moving. So they're just vibrating, but they're moving in a fixed position. In a liquid, they're able to have what we call translation. They're able to move past one another, kind of slide past one another, but they're still attracted to one another a little bit, okay? In a gas, all of that attraction is gone, and they're able to spread out and move apart, okay? But they're all vibrating at a certain amount, depending on how much kinetic energy they have. And if you've studied anything like in early, like middle school, anything like that, you might have heard of kinetic energy. So that they call that energy of motion, okay? They have, kinetics means movement, okay? So they have kinetic, kind of like physical therapists, kinesiologists you'll hear about every once in a while, where they work on movement and motion for people. So kinetic energy is energy of motion. You also have things called potential energy, which is stored energy. So stored energy is like, okay, I've got this pen that's up here. It's got stored energy, okay? I gave it energy. I moved it up here, okay? Right now, it has potential energy, okay? If I let this go, it's going to fall. So right now, the energy that it has is called gravitational potential energy, because gravity is going to pull it down, okay? When it's in motion, they're falling. That's kinetic energy. But everything, no matter whether it's falling or stored or anything, everything still has this vibration going on, okay? Certain things have more depending on what their temperature is, okay? We also talked in there about compression and expansion. So when you compress things, it squeezes that empty space out and it pushes the molecules closer together. You're going to have a higher pressure here. And we're going to talk about this more when we get into the next chapter. Diffusion and effusion. If you took biology, you know about diffusion. It's the movement of a material from an area of low concentration or high concentration to low concentration. Okay, remember that? Osmosis is the diffusion of water. It's a special case for that. And then effusion is out of a tiny hole, like if you have a puncture in your bicycle tire. That would be air slipping out a tiny hole. Or if you popped a balloon, typically same idea. Okay? Graham's law here says that heavier things are going to diffuse slower than lighter things. Okay? I'm going to run around the track a lot slower than somebody half my weight, probably. Okay? For many different factors, but weight is one of them. All right. Gas pressure, then, we're going to talk about that. That's force per area unit, and it's going to be exerted by molecules in the container. So they push out on the container. That's why when you blow up a balloon, the molecules are pushing out on that container. Now the container for the balloon is flexible, so it's able to grow to a certain point, but then you can't exceed that and the thing pops. We also have something called air pressure, where we have the layers of air that are pushing down on us, and the molecules are there. So for example, if we're way up here, like when I was in the airplane, I was up here, I'm going to have much less air pressure up there than I would down here. I'm not going to have as much stuff pushing down. So here's my airplane, I guess, is right here, okay? So I'm going to have much less air molecules pushing down on me. And you'll notice this, you also have less things dissolved in that air, such as oxygen. So if you go up, like these people that climb Mount Everest, typically they will take oxygen with them because there's not a lot of oxygen molecules up there for them to breathe. And they start sucking wind. Even if we go from here to Denver, if we're not in really, really, really good shape, you climb a set of stairs in Denver and you've been living here, you're going to be sucking wind. Okay? Because there's less oxygen dissolved in that air. That's why on the airplanes, they have oxygen masks. Because if you lose pressure up here, you're not going to have that oxygen dissolved in the air that you need. You're not going to have enough oxygen to breathe. That's why your pilots have those special oxygen. They have the military type oxygen masks that fit tight over their faces. That's why you won't see your commercial pilots with beards. Because they have to be able to fit tight over their face, be able to have that work properly. Because you want them to be able to breathe for sure, right? Those guys, you want them to have enough oxygen. When Alex was training, they actually took him up to North Dakota and they put him in this air pressure chamber, and they took it down to the pressure that it would be at, just so that they could kind of experience that feeling without having that oxygen. So it was kind of cool. We can measure pressure then with a barometer. You can measure blood pressure with a sphygmomanometer, is what this is called. Typically, pressure is measured in pascals, atmospheres, millimeters of mercury. We're going to learn to convert all of these different things. They're pretty easy. It's not that bad. I give you the conversion factors. Dalton's law of partial pressure says that in a thing where we have mixed gases in there, like air, all of the partial pressures of each gas will add up to be the total pressure. Now, this is intermolecular forces. This, I think, is fascinating because this is going to explain why this desk is solid, why this air is a gas, and why my coffee is a liquid. Okay? It's just fascinating. I mean, if you think about like why certain things are solid liquids, you probably never like really thought about, like why is this thing like this? I find this fascinating. So the reason why things are solid liquids or gases has to do with something called intermolecular forces. Now, if we look at that word inter, okay, the prefix inter means between. So this is between molecules, not within the molecules, but between them. All right. So I want to start out with a discussion of this chart and kind of look and see what you see strange about this chart. So what is it about this chart that you're like, I don't understand like why that deviates or why it's different than what the trend should be. So what do you think the trend should be, or what do you think should be different about this table? So what's weird? Well, that's what I'm asking you. What looks weird here? Well, but look at the lines. Like, what would you expect to happen when you see a graph typically? What do you expect to happen with lines? Right. They typically will go kind of like this one, right? So you've got, I mean, this isn't a perfect straight line, but everything's increasing, 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 right? So what's weird about this and this and this?
Like,
It decreases and then it increases, right? But it's only doing it for these three things, not for this thing, right? Isn't that kind of weird? I mean, doesn't that seem out of place to you? Like, what's going on there? Why would these three things decrease and then increase, and this thing just increase? Okay. So what we're going to do over the next couple days, and I don't know how far we're going to get between today and tomorrow. We may not even finish solving this till Monday. It just depends on how fast I get through the material. But what we're going to do is we're going to talk about why this graph looks the way it does. And at the end of this discussion, whichever day we finish it, I will come back to this graph and you'll be able to tell me exactly why that is the case. Okay, you'll be able to understand this and go, oh, I get it now. I see why these things are up here and why this thing isn't. Okay, so I want you to kind of think about this in the back of your head as we go through this, but just realize that it's going to be a process to get through this. I also want you talking to me and asking me questions along the way. And you're more than welcome to come in, you know, and visit the lecture live tomorrow and ask those questions, okay? I'm encouraging you to do so. But it will be videotaped in case you're not able to. Or you can join in 5th hour as well. I just don't know if we'll be at the exact same spot.
Like a Google Meet that we can like join your class, is that what you're saying? Like,
Yeah, there is every day. I have this open every day for you guys.
Oh, really?
Yeah.
Oh, I probably should know that.
You can either join 2nd or 5th hour. It's whichever hour you
Okay, so,
we just eat 2nd lunch, so make sure you come in right after 4th hour.
all right, so this one starts at what time?
This one starts at 8:51,
Okay. I didn't realize you did
and
that.
5th hour starts at 1:24, it looks like.
Oh, okay. And then you record it if we can't make it?
Mm-hmm.
Okay.
Yep. So, but, you know, if you come in 2nd hour and you're still confused at the end of 2nd hour, come back 5th hour, or watch the recording a couple times.
So you
Or-
do you like keep moving like every day?
Yeah.
As if we're here every day?
Yep.
Oh, okay.
For pre-AP, we don't, you're feeding into AP. Like, I don't have time to be able to you know, lose days for you guys. So
Right.
we have, unless we're doing a lab, yeah, I have to keep marching because there's no way I can possibly
Yeah, that's fine. I was
cover the
curious.
material and get you to where I need you to be for next year.
Yeah.
All right. So as I was talking at the beginning, we have intermolecular forces. That means between things. And we have intramolecular forces. Intra means within, okay? So intra is in the atom. So for example, if we have water here, are you going to let me? Yes, you're going to let me draw. Thank you. If I have water, the intramolecular bonds are within that water, okay? It's holding the hydrogen to the oxygen. It's holding this hydrogen to this oxygen. Those are intramolecular forces. We don't usually talk about them as intramolecular forces. We typically will call them something like a covalent bond, which is what we've talked about already this year. Does that make sense? Okay. So these are intra. They are very strong compared to intermolecular forces. Okay. Because if you think about it, I kind of think about this as like your arm being attached to your body, right? It's very strong. Okay. Can your arm get pulled off of your body? Yeah. I mean, if you get it into the wrong piece of equipment, you know, it used to be like, you know, back in the days, you'd see farmers walking around and they might have one arm, okay, because they were trying to clear out, you know, a piece of farm equipment. Their arm got pulled into that equipment and it pulled it off. You'll see sometimes machinery do the same thing in factories and stuff like that, okay? It took a lot of force to make that happen, okay? That's kind of like these intermolecular bonds. They're tight. They're very close to one another. They're very, very strong compared to intermolecular forces. So intermolecular forces would look something like this, where we've got a water molecule here. And we have, remember that this end of the water molecule is a negative charge. Remember we talked about polarity back in, we had polar molecules back in chapter 8, I believe. Remember that? Polar molecules? Polar molecules? Polar. This has a negative end to it. This had a positive end. We drew a line like this, and we had our arrow here. We indicated the positive end and the negative end here. Okay. Now, if I have another water molecule here, okay, remember this end is positive. This end of this molecule is negative. So what's going to happen there? There's going to be an attraction between the positive end here and the negative end here. Okay? That is called an intermolecular force. Okay? And that's kind of like people shaking hands or holding hands. Okay? It's gonna, you're still holding hands, you're holding one another, but it's gonna be easy to pull you apart compared to pulling your arm up, right? Okay?
So a magnet, for example, would be like the one where like the positive and negative, which is inter, right?
Yeah. But this is much weaker. This is like holding hands versus somebody's arm attached to their body. This is much weaker than this is. That's why I draw this with a dotted line and I draw this with a solid line. That makes sense? Dotted line versus solid line? Yep, it's going to be a weaker force compared to an intramolecular force. Okay? All right. Does that make sense in terms of kind of the difference between these? We have different types of intermolecular forces. We have things called dispersion, dipole-dipole. We have hydrogen. We have ion dipole. We'll get into all of those and talk about them coming up. Okay? We've talked about these, though. We've talked about ionic, where we transfer electrons. We talked about covalent, where we share electrons. We did that back in chapters 7 and chapter 8. Remember those? Okay. All right. So ionic compounds. Remember our ionic compounds, they're going to have a positive and negative ions. They're going to come together. Typically, they're very strong due to those high forces. And they're going to be formed by that alternating negative positive ion. Okay? They form that lattice structure. Remember that? Where we had like our salt, we had our chlorine, we had our sodium, we had our chlorine, sodium, chlorine, and this is a positive, negative, positive, and then we had our chlorine here and our sodium here. Remember that lattice that it would build between those? Okay. At room temperature, these will end up being, these ionic compounds will all end up being solids because this crystal lattice is so strong. So all ionic compounds at room temperature are solids. And they are collectively known as salts. So it's not just your sodium chloride, it's any ionic compound. In chemistry, we call that a salt. It's not just NaCl, which is what you're used to calling salt in your kind of real world. In chemistry, we have different names for different things, like organic. In for chemistry means something that it does different than in the real world. For us, it means carbon-hydrogen bond, you know, in materials and that sort of thing. In the real world, like you have organic produce and stuff that doesn't have pesticides, herbicides, that sort of thing. So they have slightly different meanings. All right, but they're all going to be solids at room temperature. All right, covalent compounds tend to have low melting and boiling points in general because they have weak intermolecular forces. So it's not going to take a lot of energy to get them to change. So that's what we're going to focus on here is these covalent compounds. Remember, covalent compounds share electrons. All right, we're going to talk about intermolecular forces and right.
So it says on here, covalent compounds have low melting and boiling points in general. Why?
Because it doesn't take much energy to cause the particles to move away from one another.
Okay.
And we're gonna figure out why. I'm gonna talk about that. Good?
Yeah.
All right, so intermolecular forces are going to be between, are going to be between molecules. Okay, electrostatic means that it's going to be a positive and a negative charge that they're going to be attracted to. So a positive will be attracted to a negative, vice versa. Okay. There are 4 types that we're going to talk about in here. The first 3 are collectively known as van der Waals forces. So you'll sometimes hear them called van der Waals. Good. All right, so we're going to start by talking about these dispersion forces. Okay, and if you look at the boiling and melting points, you're able to kind of see a trend here. For nitrogen, the melting point is 63 and the boiling point 77. Now this is Kelvin. Okay, so 273 minus, no, 70, yeah, 77 minus 273. There we go. So that is negative 196 degrees Celsius. That's cold. Okay, and this is even colder than that. This guy is, you can see that they're increasing. These have what's called the dipole-dipole forces. And then these have the hydrogen bonding as well. So when you look at this, you can see that as we increase, as we add in more forceful amounts here, you can see that those are increasing, okay? So intermolecular forces is kind of what, well, it's what governs whether something's a solid, liquid, or a gas, okay? And we have two different forces at play here, okay? And it's kind of this like fight between them as to what state of matter it's gonna stay in, right? We have a cohesive, so cohesive means that you're close, right? If you have a cohesive group of friends, they're really close to one another, right? And that would be your intermolecular forces. That's what's going to hold something together as a solid. So when you have a solid, they have very strong intermolecular forces, all right? But have you ever had a cohesive group of friends and then somebody else join in, or one of them get another friend or something like that, and they become kind of a disruptive force? And then your friend group starts to kind of fracture and have problems. That's the same idea here. Your disruptive force typically will end up being thermal energy. What does that mean? Thermal energy. Heat, right? Okay? And you can think about that. I mean, if you have like a piece of ice that was in a freezer and you put it out at room temperature, what's going to get added to it? Heat, right? And it's going to start changing from a solid to a liquid. And then if you apply more heat to it, like on a stovetop, it'll change from that liquid into a gas, okay? So it's kind of this play between these cohesive forces and your disruptive forces, okay? And which one's going to win out, all right? If you've got a huge amount of cohesive force compared to disruptive, then you're going to be a solid. If they're close to one another, but the cohesive is still winning, then it's going to be a liquid. And if the disruptive outweighs the cohesive, then it's going to be a gas. Okay, does that make sense? Do I have that on another? Yeah, so. Let me see how many slides. Yeah, that's it. Okay, so I've got kind of you kind of think of it as far as solid, liquid, and gas. Sorry, guys. We're starting to get into pollen season here in Wisconsin. So inevitably, I will hit my 2 or 3 weeks where I have issues. So we have our cohesive forces. We call those cohesive. Those are our IMFs. So that's intermolecular forces. That's the abbreviation for it. Versus our disruptive, which is typically heat. Okay? So with our solid, when we look at these two things, our cohesive versus our disruptive, these are going to be much, much, much stronger. When we look at our liquid, they're going to be a little stronger. And if we look at our gas, then it's going to flip around and our disruptive is going to outweigh our cohesive. Does that make sense? I'm not the best with trying to draw on this thing. I'm still working on that. Let me see if I can make these look a little bit better. There. These are supposed to be greater than signs. So your desk has fairly strong cohesive forces. You're not worried about that thing melting on you. Okay? My coffee, however, it still has some intermolecular forces because it's a liquid in here, but there's some disruptive forces in there. And the hotter my coffee is, the more steam it's going to generate because I've got more heat in there, the more of that is changing into a gas. And that's why you're able to smell the coffee when you walk in the room. Okay? Those gas particles with my no sugar, no cream coffee because Libby's got to lose some weight. This winter weight has got to come off. Good? Okay. So the first type of intermolecular force, and again, we abbreviate these IMF so that we don't have to write it out. Typically IMFs. So if you want to do intermolecular forces, it would be abbreviated like this. It's a standard abbreviation. If you go on to college, if you go on to take AP with me, in industry, anywhere, you talk about IMFs, in chemistry, they know what you're talking about. So this is a standard abbreviation. You don't have to worry about using it. If they don't know what that is, you probably don't want to be working there. So, okay. So London Dispersion Forces. London was the guy's name. It's not after the city, it's after the guy's name. He's the one that discovered something called dispersion forces. Okay? So these are going to involve temporary dipoles. Now, remember, we got to talk about, again, what a dipole is. Okay? So when you think of the Earth, you think of the North and the South Pole, right? Okay? When we talk in terms of a molecule, we talk in terms of a negative dipole and a positive dipole. Okay? So with these London dispersion forces, remember your electrons in your molecules are constantly in motion, right? They're constantly moving around. It's kind of hard to visualize that when you think about us drawing things out, but they're constantly moving. And occasionally you will get some over here, extras, and fewer over on that side. So if you get more electrons over here than you have over there, this side is going to be negatively charged. And this side will be positively. But it's just for an instant because these things are constantly in motion, right? All right, does that make sense? This happens in everything. So any material out there, if you end up with a test question, if you end up with a homework question, if you end up with a question ever that asks you what intermolecular forces are present, the first thing you write down is dispersion forces. These are also sometimes abbreviated LDF, and that's a common industry-wide thing, okay? And that's perfectly acceptable, so you don't have to write all of that out. But everything has these electrons that are constantly in motion and constantly moving around. Okay? Does that make sense? Okay? So they're constantly in flux, they're constantly moving around, and they're going to be shifting. And so you're going to get that extra little bit of negative and the positive here. But it's going to change very quickly. Okay? So uneven distribution of electrons. It's going to create this. And then this one will make this one induce a dipole. Yeah.
Can we just put that the strength depends on the charge?
No. I don't think we're to the strength yet. Yeah, we're not there. Okay. So what the strength of this is, again, it's found in everything, okay, including nonpolar substances. So the next ones to come, you've got to have a polar substance. But this guy, everything. So anytime you're asked IMFs, you write down, first of all, dispersion forces, okay? That's the first thing you write down because it's in everything. Everything has LDF. Everything. Now, oh, Let her finish right. Good?
Not yet, sorry.
Okay.
You're good now.
Okay. So when I describe this, I talk about walking across the floor with a glass of water, right? Fairly close to the top. You've got about that much left, you know, the top. Got to be a little careful, but, you know, you can easily transport that, right, across the room. Now, if you take a pan of water, like a big, you know, bucket of water, you know, like a Rubbermaid tote or something, and you fill that up to the top with almost that, you know, with that much left, what's going to happen when you try to walk across the floor with that? It's going to, exactly, okay? That's the same idea with this number of electrons, okay? So when you look at this, if you have more electrons, there's more electrons to swish back and forth, so you're going to have a greater IMF if you've got more electrons, just like if you were trying to walk across the floor with that Rubbermaid tote of water. It's going to slosh around a lot more than just that glass of water, right? Yeah? So that's the idea when we talk about more electrons here. It's going to increase with molecular mass, okay? So these are our weakest intermolecular forces. And as that molar mass increases, they're going to become stronger, and it's going to increase the boiling point. Man. My really bad time is like end of May when the lilacs start to come out. That is my worst allergy time of the year. And it's only, you know, a few weeks here and a few weeks there. So I'm not going to go and get like allergy shots for it because it's not like a whole year kind of thing, but it's just annoying for a few weeks out of the year.
I don't know. Stuff like that doesn't really bother me. I don't know why, but
Yeah.
The rest of my family, like, they get super bothered by it too, though.
Yeah.
I'm like the only one in my family that doesn't have allergies to anything. But it's like, I know what it's like, because like, their face will get like red and like itchy and stuff. You go back for like 1
Yeah, I'm trying to figure out. Okay, I just wanted to see where I was. I wanted to see where I was at because there's certain things that I add in to this, and I needed to know which slide to add it into.
No, you're good. I'm good now.
All right, so what I like to do is I like to look at the periodic table at this point, and I like to look at chlorine and bromine and iodine. Okay, so if you look at your periodic table, you're going to see, oops, come on, you're going to see chlorine here, you're going to see bromine, and you're going to see iodine on there. Okay, remember these are diatomic molecules. So in nature, chlorine is going to be bonded to another chlorine, bromine is going to be bonded to another bromine, and iodine is going to be bonded to another iodine, right? If you look at my periodic table, you will see that the chlorine is listed in green, which means at room temperature, this is a gas. This is listed in blue, which means that this is one of the few elements that's actually a liquid at room temperature. And this guy is listed in black. He's a solid at room temperature. Okay? Now, these are all nonpolar molecules. Remember, if we look at the EMF, not the EMF, the electronegativity. Wow. The electronegativity of these, they would end up being 0 because whatever value this is would be subtracted from this value, giving us a 0 amount. So these are definitely no questions asked, don't even have to think about it. These are nonpolar molecules, which means the only thing that's affecting them are these London dispersion forces. Okay? So all things being equal, they have only London dispersion forces at play. They have similar molecular structures. If we look at their valence electrons, they all have these valence electrons sitting around them. Same for your bromine. Your iodine is going to look the same way. Okay? So the only difference here is the amount of electrons involved. Okay? So here, okay, that's where we pick up tomorrow then. Nothing. Just think about what I went through, what I talked about. Think about solids, liquids, and gases and why they're different in your world. Okay? And you have some stuff from last chapter that I need.